All right, so the next step I think to do here would be to look at the atlas that comes with this paper that describes the average across hundreds of these magnetic resonance angiograms. And so I've downloaded the files for that already, so that they were a little bit hidden away on some Figshare site, just to show you where that is. So in the Teams folder, I created this link. In my setup here, if I change directly into this folder called Atlas, a bunch of files there here. So you can either find these in Teams and put them in the appropriate folder, and look at the paper for the descriptions of what they actually contain. Okay, so they have slightly different sizes. There's one which is much bigger. So the first file, which is called TOF average. TOF stands for time of flight, which is the physics phenomenon that actually underlies the this idea of doing these MRAs. And then there's vessel probabilities, radius, and some standard deviation of the radius. Okay, so we'll have to dig into the paper to understand what those mean in a little bit more detail. But I just thought, just looking at what these images actually look like and playing around with them in FSL is the first step to doing something extra with them, maybe using this vascular modeling toolkit that we have, or comparing the data that we have from our scans to the data that's in this thing here. Okay, so the first thing I'm going to do is I'm just going to look at this vessel probabilities file. So actually I've done this before, right? So I know what's going to happen. It's just an image, right? It's a nifty image that contains a bunch of information. But in this particular case, the image we're looking at is not actually a single image that was acquired in the scan, right? You have to realize it's an average of lots and lots of images, and the numbers represent not intensities, but in this particular case, sort of some measure of probability, okay? So if you look at the intensity range of the image, it goes between 0 and 100, so it's normalized. So can you think about what this actually represents? Okay, so there's some bright spots in these images here and some darker spots here. And so one useful way to maybe think about this is where there's a bright spot in the image, if you were to go and measure another person's in another person's scan, you're very likely to hit this particular vessel because it's present in all of them. Okay, so whereas if you hit a dark spot, you're very unlikely, or actually maybe there's zero probability that you'd hit a particular vessel there. Okay, there's no blood vessels there of a particular size. Okay, so what do you think is going to happen if I change the number from 0 to 100, say to 0 to 50? Okay, so I'm going to do the typing, but I'm not going to hit return yet. What do you think is going to happen? Are we going to lose some of these things, or are we going to see more of them? And maybe you can try and think through what you think would happen and try and rationalize why you think that might be the case. Okay, and maybe you might want to even pause the video for a minute here and think about this a little bit more deeply. Okay. All right, so I'm going to hit the button now, and you can see that the range of things that you can see has changed slightly. Okay, so there seems to be more structure present. Okay, and maybe if I go to 25, then we can see even more. Okay, so what's going on here? Why can we see more of that structure here? Has that got something to do with changing the probabilities, or is it just a display thing, do you reckon? All right, so I think the best way to think about it is actually sort of a display phenomenon, because we're changing the image in such a way that the darkest thing is still at 0, but now the brightest pixel that we render is at 25. So we're using all the possible colors that we have to display things between the probabilities of 0 and 25 and 100, okay, which means we can actually see all of those fine gradations. And in this particular case, in fsleyes, everything that's above 25 just continues being as bright as it was before, okay? So we're not losing any of the information, but we are able to resolve more of the things here. So we're just changing the intensity profile around, okay? So maybe we can talk about that in a little bit more detail, but it sort of allows you to see, essentially to visualize the lower probability areas in this particular map. So there's one very cool thing you can do, even in fsleyes here, in this, change to the 3D view. So you may have done that in the lab class before as well. And what we get is one of those surface representations, okay? So the one that I created using a extra command line call, you can actually do it for lots of images. You can do it straight in the viewer. Now, the issue here is that the algorithm that gets used is a little bit hidden away from us. And I haven't played around with exporting the data files. It's definitely possible, but I don't know the command that's there, okay? And again, we can change the intensity range here. So it's inherited the values that we've taken from over here when we when we press the button. And so if I change this to 10, you can now see that we see all of the areas in which there's an at least 10% chance of hitting, essentially. It was one way to think about it. I guess I don't know whether it's exactly the precise way a statistician would think about it, but where there's sort of a 10% probability of hitting one of those blood vessels if you were in a new image, okay? And so now you can maybe also understand why those areas will become bigger, right? Because as you are changing that number to a lower value, say 5 in 100, you're becoming actually less stringent, right? So it's sort of nearly like a confidence interval in space about where you think these things should be, okay? So if I change this to 5, right, then I'm being very loose about what I'm willing to accept. If I'm being very stringent, right, if I want to be very certain that I hit a particular structure, and maybe change that back to 90, then you'll be able to see there's only very few places in the brain where I'm confident, essentially, that's going to happen based on this atlas. Okay? Right. So that's already what I wanted to show you here, right? So you can take screenshots from here, of course. You can change the color maps. So maybe you don't like black and white, but you want to do orange. Change this back to maybe something more funky. So these are all things we can use for potentially in the report writing, or making figures with several subpanels and so on, for giving an idea. Okay. So the other thing you might want to do is, now that you know what this probabilities file looks like, you could maybe look at the other files that contain information about the radius and so on, and start thinking about how you could combine this information from the atlas with a single observation, right, a single MRA that way from our particular participant. Okay, so I'm going to close the 3D viewer image here, and I'm now actually going to do something that I haven't done before, and this may break, okay, in which case I'll either erase it from the video, or I'll just leave it in there to show you that sometimes I play around with stuff and it also doesn't work. Okay, so the next thing I want to do is, because I've read some of the methods details in this particular paper, I know that these images that were combined were mapped into this common standard space called the MRA standard space. Okay, and that's a space in which lots of other atlases are also projected or calculated. And it makes it very nice to look at different bits of information that were acquired from lots of different labs and imaging centers together, because we have sort of a one convenient way of talking about the same places in space. Okay, you may remember from some of the lectures, or you may have heard somewhere else, if you come to these videos from somewhere else, that there's certain assumptions built into doing this registration. So In particular, if you use an affine transformation, you assume that in order to get from one brain to another, all the spatial transformations you need to have to do are affine transforms. So that involves scaling, rotation, displacement, and so on, and shear as well, which might not be a good model for the whole object as a whole. So, but anyway, given these limitations, it's very useful to end up in this MNI space, and people are now very sophisticated about how they actually do these registrations. So what I'm going to do here is I'm going to add a standard image, which lands me in the standard brain. And so just to see whether this actually works for this particular image, so this is collected in a completely different setting. I'm going to move it to the bottom, okay, and I'll change the vessel probabilities to be displayed in red. Okay, let's maybe be a little bit more conservative about what we're showing. You can see there's actually a pretty good match between where the blood vessels are being displayed from this template image and the actual anatomical image. Okay, so that's great. So that actually worked. So I don't have to delete that from the video. And one thing that allows us to do now is we can switch on the atlas tools. Okay, so we can now actually know where we're landing in these particular structures. Okay, so because everything is in register, this opens up a whole bunch of new things that we could do. So for example, one thing that I'm particularly interested in is the course that various branches of the arteries in the back of the head take in order to supply the visual cortex and the Calvin sockets. Right, I'll stop it right here, and then in the next recording, we'll try and make use of this image information and try and visualize them using this vascular modeling tool.